So far, we've considered springs and masses while we are modeling our system. So now we're going to add in that last element, dampers, into our consideration. So here, we're going to take all of the damping in our system, and we're going to be trying to find an equivalent damping for the system as a whole. So what we're considering as a damper are elements that are dissipating energy from our system. And largely what we consider are dampers in our system called viscous dampers. And here we like to use viscous dampers because it makes the math easier, because the force exerted on a damper is going to be linearly proportional to the velocity of the degree of freedom. And these types of dampers are going to be common in mechanical systems, in cars, and in other things where this relationship is going to hold true, or at least in the range that we're talking about, the force is going to have a linear relationship with the velocity. So the general equation that we are going to be looking at is the force in the damper is equal to some damping coefficient C times now an x dot term. And these are all going to eventually be equivalent terms when we look at our model system as a whole. So while mathematically it's really convenient to use viscous dampers, and they do come up a lot, another type of damping or dissipation of energy from our system is going to come in the form of dry friction or Coulomb friction from two dry surfaces rubbing together. Now, this is mathematically harder to work with because we don't have this nice linear relationship between the force and the velocities. With dry friction, it's going to be a constant force, and it always opposes the direction of motion. So with the viscous damper, the force increases with velocity, and here, no matter what the velocity is, if it's greater than 0, the force due to friction is going to be constant. So one way mathematically we're going to be able to model this in the future is that it's some equivalent damping coefficient times basically a number that is either +1 or -1. So one way to be modeling that is taking the absolute value of our velocity divided by the velocity itself. So what this is essentially doing is it's normalizing it, so it's always going to be ±1. Now, I'm not going to go into much detail right now about Coulomb friction, but we'll get into it later. How do we model it? How do we solve for it? Because again, it makes the math much more complicated because it makes the equation of motion nonlinear. So for the time being, we're going to stick with viscous damping, or times when the force is linearly proportional to the velocities. So when we have things that have viscous damping, or at least behave like they have viscous damping, then we can incorporate it into our equation of motion through Lagrange's equations like we've been doing before. So we're going to have another term. We have the V, the potential energy, the T, the kinetic energy, and now we're also going to want to calculate R, the Rayleigh dissipation. So the format of it is going to look very similar to what we had for V, which is typically things like 1/2 kx squared if it's spring potential energy. Or for T, we had 1/2 mv squared or 1/2 j omega squared for translational or rotational kinetic energy. For the Rayleigh dissipation, it's going to look similar. We're going to have 1/2 times c x dot squared. So c is going to be, for each damper, its damping coefficient, and then the relative velocity of it squared is going to factor into this R calculation. And then where this R is going to come into play is in this general Lagrange equation for non-conservative systems. So highlighted in yellow here, this is the equation that we can always start with when we are trying to develop our equation of motion in our system. Again, I'll note that this very general form here is now accounting for undamped systems or damped systems. If it's undamped, R is going to be 0 and just drop out. But now if it's damped, we'll have an R. Our right-hand side, we can have an applied force, but this also works for autonomous systems because the right-hand side would just be 0. And this formulation works whether our system is linear or nonlinear. Once again, we're going to stick to mostly linear systems in this course, so the equation of motion that comes out in the end will be linear, but if we can formulate the T, the R, and the V, if it takes nonlinear elements, we can still do this partial differentiation and get out a nonlinear equation of motion in the end. So notice the two extra terms compared to what we saw before. We have this del t del x term, which is going to be taking our kinetic energy and differentiating it with respect to position. And now we have this r term as well. Typically, for the systems we're going to be looking at, our kinetic energy is not going to have an x term in it. It will typically only have x dot terms or first time derivative terms. So almost always that term is going to be 0. But just be aware, if you get to a more complicated type of system where you have kinetic energy that is going to be dependent on velocity and position, we do need to account for that second term when we are deriving the equation of motion. But in this course, typically that's going to be 0. So we're taking these three partial derivatives based on the t, the r, the v that we are deriving in the modeling step. So what's going to happen in the end here is after we do all this differentiation, we're going to get an x double, if we're in a linear system, we're going to get an x double dot term preceded with a coefficient. That coefficient is going to be the equivalent mass of our system. We're now going to get an x dot term that is coming from the Rayleigh dissipation. So we're going to get the coefficient in front of that is going to be our equivalent damping. And then from differentiating v, we'll get an x term with a coefficient in front that's going to be our equivalent spring constant. This m, this c, and this k are going to be the equivalent parameters that we're going to be used in solving our system. So any linear mechanical system is going to, in general, look like this. An mx double dot plus cx dot plus kx equals f. And we can modify it further. If it's autonomous, the f will be 0. If it's undamped, then the CEQ will be 0. We will be left with just an x double dot and an x. So at the end of any modeling step, this is what we're looking for, is what does this equation of motion look like? And then in subsequent sections, we're going to be looking at, once we have this equation of motion, once we have this ordinary differential equation, how do we go about solving it so that we know the position of our degree of freedom at all points in time?